Let's look next at rotational energy. Let's consider a rigid body that is rotating about an axis through the center of mass. We can find the rotational energy of this rigid body by first identifying individual particles within this mass, or we can think of the mass as if it's made up of individual particles, and then we can calculate the kinetic energy of each of these individual particles as it rotates about that axis. So we can do that as shown below. So we take an arbitrary shaped rigid body, and let's say this is the location of the center of mass of the rigid body. So if we think of this rigid body, let's consider various particles within this rigid body. This is particle M1, let's say this is M2, and this is, say, Mn. Each particle is located at its own position R1, this is R2, and let's say this is Rn. So we can say the kinetic energy of this rigid body is in general given by half mv squared. And so the kinetic energy total is equal to the kinetic energy of each element of mass in this body. And let's say that the body rotates. So suppose this body rotates with angular velocity omega. Then we can say that for each element, the speed of that element is given by v equals r omega, where r is the distance from the center of mass, and omega, of course, is our angular velocity. So that we can say that the kinetic energy total is equal to kinetic energy 1, which is half m1 v1 squared plus half m2 v2 squared plus half mn vn squared. And since v is equal to r omega, then the total kinetic energy can be written as half m1, and this is r1 omega squared, plus half m2, this is r2 omega squared, plus half mn, this is rn omega squared. So we can now write this in a condensed form as half, let's put omega squared here, and then we'll take the sum from 1 to n, mi ri squared, like that. So in this formula, the quantity in parentheses is called the moment of inertia. We use the letter I to represent moment of inertia. So we can say that the moment of inertia I is equal to the sum from 1 to n mi ri squared. Moment of inertia is equivalent to mass in rotational motion. So we can now write the total kinetic energy of this rigid body as half I times omega squared, where I is in the units of kilograms meters squared, and omega is radians per second. So that gives us the kinetic energy in joules. So we can say this is rotational kinetic energy, and it's equal to half I omega squared. If the object has both rotational as well as translational kinetic energy, then we just include the translational portion of the kinetic energy to it, and that will give us the total kinetic energy of the object as it rotates as well as translates. And if during rotation the object moves up, then we can include the potential energy, and that will give us a total mechanical energy for the system. So let's look at that. So we can say that the total mechanical energy, we write it as U, sorry, not U, but E. We write it as E mechanical is equal to the rotational kinetic energy plus potential energy U gravitational. And this can be written as half I omega squared plus mgh. This gives us the total mechanical energy if the rotating body goes upwards by height h during the rotation.